Hello friends, let's start with the second video on the shear force and bending moment diagram, and this topic is related to strength of material. These are the parts that we have already covered in last video. You can see that video link in the description box. So today we will discuss about the next topic, that is differential equation of equilibrium for beam element, means a relation between rate of loading, shear force and bending moment. So here we will see the differential equation for the loading, shear force and the bending moment or the bending moment. Okay, so first we know that suppose if any simply supported beam is given over here, and let's say this type of loading is also there. Okay, whether that loading is point load or the UDL or uniformly varying load. Okay, whatever loading is there, generally what we are considering, if any beam subjected to a loading, so we are taking a small section. Okay, we know that mathematical term, in mathematically we are considering one small element and we are taking the differential equation on that small element. Okay, so same thing we are doing over here. We have considered one beam and just consider this dx as a small element. Okay, and if we consider that dx as a small element, so we can see this type of behavior in the small element. Okay, see here dx. Okay, so on this dx small element, shear force and the bending moment will produce. Okay, shear force and bending moment will produce. So if we consider on the left side, so positive shear force and the positive bending moment, and as a differential equations we are considering on right side, just consider v plus dv and m plus dm. So this is a small element that we have considered. Okay, and we will start with the differential equation. So first thing is what, when we are taking derivative of moment with respect to x, then we will get the shear force. Okay, derivative of moment with respect to x, we will get shear force. And if we go with the slope diagram, so slope of bending moment diagram gives the shear force at a section. Okay, means suppose if any bending moment diagram we are considering, and if we consider the slope of that bending moment diagram, that slope is indicated as a shear force. Okay, slope of bending moment diagram indicates a shear force. Then second, if we take the derivative of shear force with respect to x, then we will get load. Okay, derivative of shear force with respect to x, then we will get load or the w, and the slope of SFD gives the intensity of loading at a section. Okay, means if you have taken any section and if you consider the slope of that SFD diagram or the shear force diagram, we will get the loading at that particular section. Okay, next, these points are most important for the competitive exam. So just remember this. Yes, in day-to-day academic, it's not that much important, but in competitive exam it will most beneficial. Okay, so w dx equals to w, means when we are considering derivative of w with respect to x, then the area of loading diagram between two sections gives a change in shear force. Okay, area of loading diagram between two sections gives a shear force. Okay, means suppose if we consider this diagram or this small element, and if you take the area of this portion, so between that area we can calculate the shear force. Okay, and this is general formula. If we take the integration, okay, integration of w with respect to x, then we will get the difference of the shear force. Okay, same thing. Suppose if we take the integration again, okay, area of shear force diagram. Now if we go with the area of shear force diagram between two sections gives the change in bending moment. Okay, then it will give us the change in bending moment, and then change in bending moment we can consider like, okay, in simple thing, derivative of moment will get shear force. This one first equation, the first equation indicate derivative of shear force, we will derivative of moment we will get shear force, derivative of shear force we will get loading, integration of loading diagram we will get shear force, and the integration of shear force diagram we will get the bending moment. So these are the four equations, or we can say the differential equations, that we need to consider for the calculation of shear force bending moment diagram, or to derive the equation for shear force bending moment and loading. So how we can take it, that we will see in the numerical, but now theoretically this point is most important, so keep in mind. Now next step is general step to draw a shear force diagram and the bending moment diagram. These are the general steps. We will see in brief how that steps are we can implement in the numerical. But the simple step is what? First, draw FBD. FBD means free body diagram. FBD means free body diagram. Then second, find the shear forces at the each point. Then find the bending moment at each point. Then draw SFD and BMD. Then find the point of zero shear, if any, and find the maximum bending moment. Sixth one is to locate a point of contraflexure, and the next one is the deflected shape. Okay, these are the 7 steps that we need to follow for the calculation and for drawing SFD and BMD. So we will see in brief how we can consider each and everything in each step. Okay, now we will see the general steps to draw the shear force and bending moment diagram as we discussed in last slide. The first, we need to draw free body diagram. Okay, free body diagram means what? If any simply supported beam is given, let's say this is simply supported beam carrying UDL on entire span. Okay, W is there, and let's say suppose this reaction here hinge, and then here roller support is given. So in that case, first we need to free body diagram. Free body diagram means what? Just we have to consider the reaction at the support. Okay, so free body diagram is like this. Okay, reaction at this point, reaction at this point, and this total beam carrying UDL on entire span. So this is a simple thing. Okay, that we need to consider in the FBD diagram. Okay, and then once you draw the FBD of the given diagram, then calculate the support reaction by using equilibrium condition. Okay, so we have 3 equilibrium conditions that we have discussed in last video. Summation fx equals to 0, summation fy equals to 0, and summation m equals to 0. Okay, so just use that equilibrium conditions to calculate support reaction. The next, divide beam into segments. Okay, so whatever beam is given to us for the calculation, first we need to divide that beam in particular segments. Okay, by observing how we can divide it in the segment, by observing the changes in the loading rate and change in cross section of the beam, if any. Mark the different segment of the span of beam by using alphabets A, B, C, D, and so on. Means what? Suppose if any beam is given to us, okay, suppose this beam is given and one loading point load suppose is given. Okay, so first we need to divide the total beam in a particular segment. Okay, the first thing is what? That segment is maybe on the rate of change of load. Okay, so now here we can see at this point simply supported one support is there, this point is also support is there, and here is the one loading. So we can consider AB as a first section and BC as a second section. AB first section, BC second section. Why we have considered these two different cases or two different segments? Because one point load is there. Suppose if any point load is given over here, let's say P, so again we need to consider point at the point load, let's say D. Okay, so here we are considering AB first, BD second, and DC third segment. Likewise, we have to divide our beam in particular segment if that points are not given in the numerical. Now next point is what? In the cross section of the beam. In the cross section of the beam means what? Suppose the different cross sections are given for the beam. Let's say this is our beam. Okay, and these two cross sections are given. Here we can see the depth of beam is different. Let's say D1. Okay, and at this position depth of beam is different. Let's say D2. So in such case, again we need to divide this beam in two segments, AB and BC, because at B point suddenly area or the depth of beam has changing. So in that case also we need to consider the different segment. Okay, so like A, B, C, D on the basis of loading and on the basis of area, we need to divide the beam in the particular segment. Now after that shear force calculation. Okay, using proper sign conventions by taking a section at each segmental point and considering either left or right of section, find the algebraic sum of vertical or the lateral forces to obtain shear force at a section. For simplicity, always take a left FBD for the calculation. It means what? Whatever segmental or FBD diagram we have drawn, okay, whatever segmental or FBD diagram we have drawn, so we need to consider the proper sign convention first. Okay, the first thing is what? Consider the proper sign convention. And the proper sign conventions already we have discussed in last video. Okay, so as per that sign conventions, we need to calculate the shear forces. So how we can calculate the shear forces? Okay, taking a section at each segment. Now, suppose these are the two segments AB and BC. So we need to consider the section in first segment, then calculate the shear force. Okay, then section in second segment and calculate again shear force. Okay, so while calculating shear force, always start from the left calculation. Always start from the left to right of that FBD. Okay, always start from left to right. But actually, that direction means left to right or right to left is totally depend on the supports. Okay, let's say here we have the simply supported reactions on both sides, so we can start from left or right, no problem. But if any fixed support is given, let's say at a point fixed support is given, so in such case we are unable to start, or we cannot start our shear force calculation from left because fixed support is there. Okay, and at fixed support we have some unknown reactions. Okay, and we will not get a perfect value of shear force. For that case we need to start from the right. Okay, so from any point you can start from left to right or right to left. Okay, that's up to you. But if fixed support is not given in the beam, in that case always you should start with the left. That will be what you can say easy for the calculation. Okay, then one word is there, that is algebraic sum of vertical forces. Algebraic sum means what? That is the plus or minus you should consider as it is. Means suppose if any force is going upward, consider positive. Force is going downward, consider negative. So plus minus, okay, take the summation algebraic sum of that forces, means with their direction and their sign we need to calculate shear forces. Okay, now, once we calculate the shear force, next plot SFD starting from the left or right as per diagram and join the points with the proper form of line. Okay, means suppose here we have calculated, let's say at this segment, just we have discussed simply supported beam centrally point load. So we have these 3 points. Okay, so we will get the reaction or the shear forces at A, B, C, all points. Okay, so next step is what? Just plot or just draw the point for the shear force diagram. Let's say we have shear force at this point. Okay, something. Okay, here something value and here something value. So just draw these points as per the values. Okay, if that value is 0, so we can start from this. Okay, it's depend on the answer that we will get in the shear force calculation. Okay, and after that draw or join that line, join that joint by using the lines. Okay, whether that line is a straight or the parabolic curve. Okay, straight or parabolic, that is depend on the loading that we will see in the numerical how we can draw it. Okay, but we need to just draw that points by joining all the points. Okay, that is the shear force calculation and the shear force diagram. Next is the bending moment calculation. Again, for the bending moment calculations, we need to use the proper sign convention by taking a section at each segmental point. Now here we have to consider the segment at each, we have to consider the section at each segmental point. Okay, means suppose these are the A, B, and C. Okay, these are the 3 points. So instead of taking section at segment, we need to consider the section at segmental point, like at A, at B, and at C. So that is the main difference in shear force and bending moment calculation. In shear force and bending moment calculation, in shear force calculations we are considering section in the segment, and in bending moment calculation we are considering section at the segmental point. Okay, that is the main thing. Consider either left or right part. Again, same thing as we discussed in shear force calculation. You can start that calculation from left to right or right to left, but it depends on the fixed support. If fixed support is there, so always we need to start our calculation from opposite to the fixed support. Okay, but one thing is, remember, just for practice or keep in mind for the calculation, if we start shear force calculation from left to right, so in bending moment also we need to start our calculation from left to right. The same thing is there. Okay, we need to consider. Okay, now find algebraic sum of movement due to forces to obtain the bending moment at a section. Plot MBD, means plot BMD means bending moment diagram starting from left and point with a proper formed lines. Okay, again take algebraic sum of all moments. Suppose you have a three movements, three forces, so you will find three movements of that three particular forces and then take the algebraic sum that we will see in the numerical. Okay, then calculate maximum bending moment value in a segment. Okay, so once you calculate the shear force and bending moment diagram, the next step is what? Consider or the calculate the maximum bending. Generally, the maximum bending moment is at the zero shear point. Okay, means if any particular segment having zero shear, at that point your bending moment is maximum. Okay, at that point your bending moment is maximum. So we need to calculate that bending. Okay, let's say suppose if we go with the one simply supported beam. Okay, this simply supported beam carrying UDL on entire span. Okay, that we will see. So the shear force diagram is like this. Okay, so at this point our bending moment is maximum. So first we need to calculate that position of shear force. Okay, means the distance of that shear force from any support and then calculate the bending. Okay, so we will see that one by one in the numerical, so that will clear to you. Then distance x in such a segment as we discussed. Okay, for this simply supported beam. Okay, the shear force zero at this point. Okay, shear force zero at this point, so the bending moment is maximum at that point. So what we need to do, we need to calculate the distance of that point by considering, let's say this distance is x. Okay, this distance is x, so we need to calculate that. Write equation of bending moment for this equation. So now here just take the one section. Okay, and take the moment about that section. Okay, suppose one force is there. Suppose we have taken section over here, this distance is x and ra reaction is there. So what will be the mx is equals to rx into ra into x. Okay, ra into x, then this w. Okay, that is minus w x into x by 2. How to calculate it, that we will see, but it just for understanding I am doing it. So this is our equation, ra into x minus w x square by 2. Okay, so now here we are getting this equation. Just put the value of x, we will get the maximum bending. And in first step we are calculating the value of x. So how to calculate it, that again we will see. Okay, then next find x. So how we can find x? We know that the derivative, whatever moment equations that we have considered. Okay, whatever this one, this equation, mx equals to rax minus wx square. So if we take the derivative of this equation with respect to x and equate it to the zero, we will get the value of x. And once we get the value of that x, just put in the equation, we will get the maximum bending. Okay, that is a simple thing. Getting the value of x and substituting in the equation of m equals to fx, we get the maximum value that we have discussed previously. Okay, then locate the point of contraflexure. Okay, locate the point of contraflexure. So this is also called as point of inflection, where a bending moment changes its sign. Okay, so what is meant by contraflexure or inflection? So if any diagram, in any bending moment diagram, if your bending moment is changing their sign, bending moment is changing their sign, let's say it is positive and it is negative, so in that case this point we can call as a point of contraflexure or point of inflection. Okay, so in short term we can say where the bending moment is zero, that point is a point of contraflexure or point of inflection. 2 points are there: zero shear point where shear force is zero, and point of contraflexure means bending moment is zero, like this. Okay, now take a section at a distance x. Same thing. Okay. In which sections we are getting the bending moment is zero, so we need to consider the section at that point, then consider the x distance, then again write the equation for the bending moment by taking the moments. Okay, find the x where moment is zero. Now in this equation your bending moment is zero, so that equations, whatever equations we will get in the form of x, that equation we should be equals to zero, we will get value of x. And once we get the value of x, then that point is indicated as a point of contraflexure. Okay, now next step is what? Last step, deflected shape. Okay, means elastic curve. Just draw the deflected shape. Okay, by observing the nature of bending moment diagram, means sagging or hugging, we should be calculate the deflected shape or the bending moment diagram for the particular beam as per the loading. So these are the simple steps that we have discussed: how to calculate the bending moment diagram, shear force diagram, okay, and how to calculate the zero shear point position and the point of contrafracture positions, maximum bending moment. So everything that we have clear. Now in next video we will start the shear force and bending moment diagram of uh, some standard cases. Okay, like simply supported beam centrally point load, simply supported beam UDL or test span. So that simple numericals that we will see, and then we will proceed for the higher level numericals. Okay, so if you like this video, already I have uploaded a few videos on the stress and strain, okay, unit, some numericals and theoretical parts that I have covered over there. And now I have started with the shear force and bending moment diagram. This is our second video, and if really you are getting some benefit from these videos, so please like, subscribe, and share this video to your friends so they will get benefit from this video. Thank you.